Hi, you've obviously made it to Unit 3. I want to talk a little bit about a little review on vectors. I know I gave you that information for summer assignment, and knowing that most of you have already been exposed to some stuff on vectors, we didn't cover that in great detail. So this will be a little bit of refresher on that, but stuff you probably already know, and we're going to relate it more to two-dimensional motion and projectile motion. Let me just say, if you haven't already looked at a movie that I've already made for motion in two dimensions. Go back and look at that first before you come into this little PowerPoint video. I think that'll give you a better idea of what we're talking about before you start looking at some of these concepts. We did some sample problems with a boat going down a river, and then a ball rolling off a cliff, and finally an arrow that shot into the air. So if you haven't already seen those, I would pause this now and go find that video. It's in the concepts folder for this unit, motion in two dimensions, so check that out. Okay, so quick review on vectors. Remember, vectors are arrows. They represent quantities that have both magnitude and direction. Things such as velocity and acceleration and force would be represented as vector quantities. Scalar quantities are things that are defined only by a magnitude or only by an amount. So things like mass or time would be considered scalar quantities. We can do mathematical calculations involving vectors and scalars at the same time. So for example, you can take a vector and divide by a scalar. Numerically that's pretty simple, but visually sometimes that's a little misleading. Okay, remember, technically vectors are only equal to each other if they have the same magnitude and the exact same direction. I will use terminology saying that they're equal, or I will try to say same magnitude. For example, when I'm talking about two opposing forces, a force of 10 newtons east and a force of 10 newtons west, that cancel each other, I will try to refer to those two things as having the same magnitude. But don't be surprised if I slip up and say that the force to the left is equal to the force to the right, meaning that they're equal in magnitude. And the second point here says movement of vectors in a diagram. Any vector can be moved parallel to itself. This is simply what we do when we start with a point diagram, and then I can pick up one of the vectors and turn it into a head-to-tail diagram, just so that the visual representation looks more like what we're trying to do mathematically. So if I'm using Pythagorean theorem to solve a problem, I may pick up a component vector and move it to the other side to produce a head-to-tail diagram, just so the triangle is easier to see in the diagram. Not too worried about definition of negative vectors. Make sure you know what a resultant vector is. We'll be dealing with those all year. Even when we're in electricity and electrostatics, we'll still be dealing with resultant vectors and velocities of those tiny particles as well. So resultant vector is kind of like your answer vector. It's a sum vector. It's what really happens if we're talking about force or velocity. The direction or the velocity of the object is really traveling, even though we might break it into components, or we might be combining components. So in the case of the arrow going through the air in the last tutorial, we took that actual motion, the resultant, and broke it down into two components. Whereas with the boat traveling on the river, we took the two components and combined them into the resultant. But in both cases, the resultant was either the real velocity and direction of the boat or the real velocity and direction of the arrow. Two different ways we'll add vectors. We'll do them algebraically, and we'll also have you do just a little bit of practice adding them pictorially or geometrically. Whether adding vectors geometrically or algebraically, one thing to remember is you have to have the same units. You can't take a force vector and add it to a velocity vector in a diagram, or likewise algebraically. So they have to be the same units. Geometrically, we have you do a couple of these problems for homework, and then we won't be doing any more of this. I've seen a question once show up on the AP exam like this where they actually wanted you to just do it through a diagram, but usually not. Usually we're doing the vector addition algebraically. But for your homework, there are a couple that require you to do that. So you may get to the point where if you haven't paid attention to the directions for the homework assignment where it says to do it graphically, you may get to a point where you realize trigonometrically or algebraically you can't solve it. That's what they're asking you to do, is just use a ruler and a protractor, draw them to scale, and then estimate the length best on of the resultant vector based on your most precise based on precision with your instrument to the best you can. So here again is your picture of a head-to-tail diagram, or a tip-to-tail diagram as it's sometimes referred to, showing the resultant of A and B added together. And I had you in the summer assignment work on a couple of those, giving you some angles to come up with the actual resultants algebraically and using your trig. And likewise, most of you should be aware that we can add multiple vectors, especially when we're dealing with force or displacement. Oftentimes with velocity, we're only dealing with two, but more often with force and with displacement, we're dealing with multiple component vectors, not just two. So this would be an example of such where we've added 4 different vectors together to come up with the resultant. And if these were displacement vectors, and this, I think I mentioned this before, but my grandmother always referred to this as the way the crow flies, you know, being that if you had to take a certain path through some trails or through some streets and woods to get from one place to another, you probably wouldn't be able to travel in a straight line, but a crow can. It can take off at any spot and fly directly to another spot. And so our resultant vector is kind of like the way the crow flies. She would always say, well, it's 16 miles from here to there, but it's probably only about 12 the way the crow flies. So talking about the comparison of actual displacement and the driving distance. So I guess Grandma knew more physics than she thought, but she's not around to ask her at this point. So vectors obey the laws of addition, commutative law. 3 plus 7 is 10, and 7 plus 3 is 10. In the same way that a plus b is the same as b plus a when we're adding vectors. It doesn't matter the order that we add them. And in fact, when we're talking about forces, typically there isn't an order. Both of the forces, for example, if 2 players kick a soccer ball at the same time and we want to know which direction the ball goes and with how much force, there isn't a first vector and a second vector. It's happening simultaneously, so it's kind of the user's choice in that case. We won't refer too much towards subtracting vectors, but remember that's simply vector addition in the negative direction. Most times we'll have the actual vector drawn the opposite direction. We're just adding a negative vector, and we won't refer to subtraction. So here's a case where the mathematical representation of the vectors doesn't really fit physics, because we would be talking about the actual vector being in the opposite direction. We're not going to have 2 players kicking a soccer ball and we're needing to calculate, well, what if this person kicked it the opposite direction, you know, when they didn't. So vector subtraction won't usually apply in our real world situations, but just an example of what how you would interpret it mathematically, I guess. Again, you just draw them tip to tail. We draw A first, then we draw B, and our resultant is start wherever you drew A and wherever you finish drawing B, and that's your resultant. Again, if we drew these to scale with a ruler, and ruler, say, you know, you picked a unit such as a millimeter representing 1 Newton of force, and we drew in our angle perfectly of the two vectors, then our AB vector, we should be able to measure it with a protractor and with a ruler and come up with the same value you would get if you calculated algebraically instead of geometrically. Okay, so again, hopefully you've already looked at the motion in 2 dimensions video that I had previous to this on the website. Here's our component vectors. Again, we're taking a vector and breaking it down into 2 components that fit our coordinate system. Typically, we'll use a Cartesian coordinate system, so we have x and y graphically. And when we have a vector that doesn't fall directly on an x-axis or directly on a y-axis, and we need to combine it with another vector, usually what we will do is break it down into an x and a y component, and then we can break our second vector down into x and y components. We can add them then by adding the 2 x components or subtracting them if they're in the opposite directions, and adding the 2 y components, and then combining those 2 y resultants and x resultants together to come up with our final result. And I did an example of that using, I believe it was a sled in the summer assignment folder. If you go to the concepts folder for summer, you'll see that sled problem again, and probably recall that from just a few weeks ago. So if you're not remembering that, there's a good example of that where we calculate the direction, the speed the sled goes when 2 different people are pulling it at 2 different directions. And of course, we use our trig to calculate these 2 components, where the a vector, the ax component would be calculated if we look at a triangle. Let's pick up ay and move it over to the other side so it's tip to tail with ax. We can calculate ay based on the cosine function, where the cosine theta would equal ax over a. And we can calculate then ay, where ay would be equal to the, using the sine function, where sine theta would equal ay over a. Or in other words, AX equals A cosine theta, and AY equals A sine theta. So again, if you recall the sled problem, essentially what we're doing is we're taking two forces. Two people were pulling the sled at the same time. Both of them were an angle to the vertical, the way I drew it. And so we broke down both forces into x and y components. We added the y's together, and we subtracted the magnitude of the x's. And this is what this is referring to here, where you add all of the x components, and this gives a resultant in the x direction that's equal to the sum of all the x components, or x velocities. And then we would likewise add or subtract all of the y components of the resultants and combine them to get the final resultant using Pythagorean theorem. So again, if you're not recalling or not understanding exactly what I'm talking about there, go back to the summer folder, and in the concept section you should be able to find a tutorial example problem. I did it on the chalkboard in the video with two persons pulling a sled at the same time at two different angles to the y-axis. Through in this slide is a reminder of your SI units. We'll do displacement always in meters, average or instantaneous velocity always in meters per second, and average or instantaneous acceleration always in meters per second squared, which really represents a meter per second per second. So again, acceleration is change in velocity. Velocity is measured in meters per second. So we look at how our meters per second of velocity change per second. That's where the seconds squared come from. I always want to make sure I cover that because I took physics for an entire year, and all I knew is when I calculated A, I put meters per second squared behind it, but I had no idea what a meter per second squared really was. You can visualize a meter per second, an object rolling exactly 1 meter every second, but how do you visualize a meter per second squared? And I always visualize it now as watching a speedometer on a car, and if I have a speedometer that measures meters per second, that every second the needle would be changing. Let's say we're accelerating 5 meters per second squared. I'm watching the speedometer on the car, and it's pointing at 5, and now it's pointing at 10, and now it's pointing at 15, and it's pointing at 20 meters per second. So it's changing by 5 meters per second every second, and that's where the second squared comes from. Okay, here are our big assumptions with projectile motion. Essentially, we're looking at free fall. Remember we said things are in free fall whether they're going up and down or if they're coming just straight down. Normally when we think of falling, we think of down, but technically an object that's moving upward and only under the influence of gravity is still in free fall. So our projectiles are technically just objects that are in free fall, and in this case we tend to think of them more as things that go up and back down while they're also moving horizontally, but they don't have to. So problem we did previously was an example problem for Unit 2 with one-dimensional motion. I think I did a sample problem from the Giancoli textbook where we had a stone that we threw upward from a cliff, went up in the air, and then it came down, just barely missed the cliff, and fell another 70 meters down. So that would be an example of projectile motion even though the object is not moving in the horizontal direction. Now if you picture doing the same thing, we're going to throw the stone up in the air from the top of the cliff. It goes upward 12 meters and then falls back down. Actually, it wasn't 12, it was 7. But anyway, it falls all the way back down then. If you picture a wind blowing it, maybe at 5 meters per second or 10 meters per second horizontally, now the object goes upward and comes back down, and during that time interval it also moves forward in the horizontal direction. That would be more of what we traditionally talk about as projectile motion. However, the directly up and directly down without moving horizontally technically is also projectile motion. And thus, I won't define projectile motion based upon parabolic paths, only based upon a free fall assumption, where the only force affecting it is gravity, because we're ignoring air resistance or any other things. Objects that would not be projectile motion are not in free fall. Obviously, anything that has its own engine, such as a rocket or an airplane, or until I guess the rocket ran out of fuel. Once it runs out of fuel or shuts off the engines, then technically it's projectile, traveling only under the force of gravity. The biggest thing you have to keep in mind with projectile motion, and this is hard to do, is that the x and y directions of motion are completely independent with each other. In other words, the fact that the object is moving horizontally does not affect how it moves vertically, and the fact that the object is moving vertically does not affect how it moves horizontally. This is in contrast to if you watch cartoons. The one I remember always was the Roadrunner and Coyote, and the coyote run off the edge of the cliff, and because he was going so fast, he didn't fall until he slowed down, and sometimes it wasn't until he actually looked down and realized there wasn't any ground supporting him that he started to fall. Just in case you're not sure, that doesn't really happen. The coyote starts to fall as soon as he leaves the cliff, and it doesn't matter how fast he's moving forward. The good thing with this, or the one thing that people always talk about, is the bullet in the gun, where I've got a gun that fires a bullet forward and at the same time drops one and wants to know how long it takes for the bullet to reach the ground, or which bullet reaches the ground first, and of course the answer is that they reach the ground simultaneously. The fact that the one bullet is moving extremely fast forward does not affect how quickly it falls. Both bullets fall under the influence of gravity with an acceleration negative 9.8 meters per second squared, and therefore both bullets reach the ground the same amount of time based upon only the height above the earth that the bullet's fired from. Again, as long as the bullet's fired horizontally. Now, those of you who know anything about firing rifles or even firing bow and arrows know that the sights for aiming at a target are adjustable based upon how far away the object is. So if I have an object that's, say, 20 meters compared to an object 50 meters, the sight for 50 meters is going to be different than the sight for 20 meters. And what the sights do, if you ever look at a rifle, is you'll see that typically the back sight is slightly higher than the sight at the front of the barrel. And what that causes you to do is tip the barrel slightly upward so that the bullet actually travels in a parabolic path as it goes to a target without taking into compensation for the falling. That way it stays in the air longer. So most people say, well, I've fired a rifle before and it doesn't hit the ground in 0.3 seconds like a dropped bullet would, and that's because you are slightly aiming upward. And that's true even if you don't think you're aiming upward. Again, the sights are adjusted on the rifle so that you are tipping upward. On a bow and arrow, the sights, there are different pins that stick out of the side of the bow and arrow. There might be a yellow pin, red pin, green pin, and I'm not extremely familiar with it. Maybe some of you are instead. But one pin's for maybe 20 yards, the next one's for 30 yards, the next one's for 40 yards, so that if you're aiming at a target, you have to estimate how far away the target is and then use the correct sight based upon how far you think the object is away from your position. That way, as you shoot it, you may be lining up with the target, but the sight you're using causes you to tilt the arrow slightly upward, so that you're actually firing it upward and it comes back down to meet the target, as opposed to pointing the arrow directly horizontal at the target where it would fall and hit the ground prematurely in front of the target. So this diagram represents an object traveling in projectile motion, showing when it's initially launched, it has a Vx and a Vy, that the Vx horizontal velocity doesn't change. So at each instant in time that we show the vector velocity, we break it into its components. And notice in each one of those 5 points along that parabola, the Vx does not change. Now in real life, the Vx would change slightly if we're firing this on Earth, because there is a little bit of air resistance depending on what the projectile is. Obviously, if it's a basketball, there's going to be more air resistance than if it's an arrow. And the actual path is going to be slightly different than the path that's shown here, which we refer to as an ideal path. But notice in the diagram, the Vy is changing. It starts off with a certain magnitude, and then it gets smaller until it's 0 at the peak. Just like when you throw an object directly upward, it reaches a 0 vertical velocity. So does the object that's in projectile motion reaches a 0 vertical velocity. It's just doing so while it's also moving forward. So the vertical motion here is the same as if I threw a ball straight up in the air and it came straight back down. The only difference is that it's drifting horizontally to the right while that's occurring. So you can picture in one instance you're going to throw a ball straight up in the air and it comes straight back down. In the other instance you throw it straight up in the air but there's a wind blowing it and it comes back down. Still takes the same amount of time to go up and down, but instead of coming back down where you're standing, it comes down in a position that's farther right based upon that wind speed that maybe has given us our Vx. One thing to make sure you know is that the maximum distance traveled theoretically is based on a 45-degree angle. That's going to change a little bit realistically based on the amount of air resistance on the projectile. If it's something that's going to encounter a lot of air resistance, sometimes a better distance can be achieved at a 40 or 42-degree angle as opposed to a 45. The other thing to point out, however, is that moving just slightly an angle above that, say we go to 50 degrees, 5 degrees above 45, or we go to 40 degrees, 5 degrees below 45, that those two should result in a distance traveled the same amount for the projectile. So in one case, we're changing the angle to 50 degrees. We're getting a greater vertical velocity, a greater Vy, which means it's going to stay in the air longer. However, we have a smaller Vx, so it's not going to move as quickly across the ground. In the other example, where our theta is 40 degrees, we would increase the Vx, so it would move faster across the ground, but now we've decreased the Vy, so it doesn't stay in the air as long as possible. So ideally, or I'm sorry, theoretically, a projectile launched at a 40-degree angle and 50-degree angle should produce the exact same horizontal distance, just different hang times. Remember, all of our same motion equations work for projectiles that aren't symmetrical. In other words, I'm not shooting it from the ground and it's coming back down to the ground. So the up-down portions are non-symmetrical in this case. We can still use the exact same vertical equations we've used in one-dimensional motion and the exact same horizontal equations we've used in one-dimensional motion. Remember, in the horizontal direction, our acceleration will be 0, or ax is 0, being that it's traveling at a constant horizontal velocity. And in this case, away from the Earth, that ay is not equal to 0, ay is equal to negative 9.8. And again, even at the top of the path, please don't fall into the misconception that acceleration is 0 in the vertical direction when velocity is 0 at the top. Yeah, I hope that helps your understanding a little bit. Make sure you've read the appropriate sections of the chapter if you haven't done so already, and bring any questions you have to class so that we can answer them and be a little more thorough. Thanks very much, and good luck.